Okay, guys, we are back with the seventh video of psychometric charts. Most probably the spelling is correct, but ignore that. And yeah, this is the correct one. Psychometric charts. And so basically, what the psychometric chart do basically? So psychometric charts are basically data for air water systems. So let's start. Let's assume. mm, Better let's define some things beforehand. So what all do we have? We have wet bulb temperature. I'll tell these terms in a minute. We have wet bulb temperature, we have dry bulb temperature, we have dew point. Dew point I already defined. We have dew point, and then we have enthalpy, relative humidity, absolute humidity, and what else? We have humid volume, and we have adiabatic cooling. Let's go through each of these terms one by one. Okay, so let's assume that there's a thermometer. There's some thermometer. There's a very bad thermometer, but yeah, manage with it. And you are keeping a cloth around it, a wet cloth, and then some air passes by. So temperature of this air is called dry bulb temperature, and then initially you are at dry bulb temperature, and due to this wet cloth, when the air passes, this is not completely saturated, so some water will start evaporating, and finally it will from where is it taking it? It's taking heat from the bulb, so the temperature of the mercury inside will come down. It will get stabilized at another temperature called wet bulb temperature. So this is the wet bulb temperature. This is how it is defined actually when you try it with a wet cloth and you continuously pass air and the cloth is continuously dry, so the temperature which at which the thermometer becomes constant again is called the wet bulb temperature. wet wet bulb. Okay. Now, where else do you say this? Let's say you are in a swimming pool. You just come out of the swimming pool. Outside temperature is 30, but your body will feel like it's 25 because that point the wet bulb temperature will be this, and this will be a dry bulb temperature. Yeah. So that's about wet bulb and dry bulb, and why it is happening that wet bulb is less than dry bulb. That air going out, because it is a big thing. It does not have any change in temperature, but why the water temperature is changing or why the bulb temperature is changing? It's basically that water wants to come in equilibrium. So at at the dry bulb temperature, at the dry bulb temperature, equilibrium is not maintained. So water temperature drops such that at the new temperature, Raoult's law is followed. So vapor pressure is extremely sensitive to temperature. So at that temperature, vapor pressure becomes equal to partial pressure. So that's mm, wet bulb temperature. So now, what does wet bulb temperature have to do with us? Why do we need wet bulb temperature in general? So basically, when you have a lot of water, it's a bit hot water. So what's the basic idea of cooling water? You pass air to it, and then air comes out. Air comes out. This is unsaturated. This comes out relatively more saturated. And from where is the water getting evaporated? It's taking heat from the remaining bulk of the water and it's getting evaporated, so the water temperature comes down. That's exactly the principle of how water gets cooled in an earthen pot. So the minimum possible temperature of water here is also the wet bulb temperature. That's one thing. Dew point, you know that if there's a water vapor and you keep on cooling it down, the first drop is formed at the dew point. Okay. Now, relative humidity is at that temperature. What is the vapor pressure? Out of that, how much percentage partial pressure is present in air, that is called relative humidity. Absolute humidity is how much vapor is present in in that air by the total mass of the dry air, and other things will come along. So let's read the chart. Okay, now let me assume that I'm having a 20% relative humidity. So this is the 20% relative humidity curve, and let's say I have an absolute humidity of 0.008. So yeah, one thing you need to make sure here, that this is on a dry basis. This is kg of water per kg of dry air, not a kg of the final thing. Yeah. So that is one point, and I get the, by taking a projection, I get the dry bulk temperature. This is around 38 or something. Yeah, 38. So that's the dry bulk temperature. Now what will you do? Now I want to find out the wet bulk temperature. So you see, okay, I need some more colors. You see these lines. These, oh, sorry about that. You see these lines, these slant lines. These are constant wet bulb lines. So basically, what you do, you take this temperature and go to the nearest. Basically, you actually consider that the wet bulb lines are almost parallel, and whenever you don't have wet bulb line, you just interpolate. So I'm going to the nearest wet bulb line over here, and then this is the wet bulb line on which I'm going to travel. So there's one question for you, that wet bulb temperature will be less or more than the dry bulb temperature. It will be less, right? So I have to travel on this side. I have to travel till the point I get to the saturation. Saturation is basically 100% relative humidity. So whenever I reach the saturation, that is the wet bulb temperature, and I take a projection down. And water temperature this is, it is 22 degrees Celsius. So 22 degrees Celsius is the wet bulb temperature. It can also be read from here. This is 20, this is 25, so this is 22. Okay, so we saw how to find out wet bulb temperature. We saw how to find out the dry bulb temperature. Now, what about dew point? So dew point is basically you have humid air. You have humid air. Let's change colors now. Red. Okay, you have humid air, and you don't change the moisture content, right? You have the same moisture content, but you just keep on decreasing the temperature. So here you are, and you need to move with the constant absolute humidity. So just move left on a horizontal line. Wherever you reach on the saturation curve, that's the dew point. See, because here I'm not changing the absolute humidity. So this point is the dew point. Okay, we define dew point as well. Now, let's say I'm already at saturation over here. So I'm defining enthalpy. Enthalpy. With the reference state, reference states are given over here. Reference state H2O, liquid 0 degrees Celsius, 1 atmosphere, and dry air at these conditions. With respect to this reference, it is told that the enthalpy is this. So I read it from the enthalpy over here. It's something around 77. 77 watt. 77 kilojoules per kg dry air. See, over here also we are defining it with respect to dry air itself. So 77 kilojoule per kg dry air. Okay. So that is the saturation enthalpy if it is saturation. Now what to do if it is unsaturated? Okay. So for that you have another curve. This is one of the most interesting graphs which I got in this course, because there are a lot of things happening in the same graph. Yeah. So you can see this nice lines. Oh, sorry. See these nice curves over here. These bent curves. These are the enthalpy deviations. So basically what you do, let's see here at this point, is the color visible? Let's see at this point, okay, and what this reads is 0 minus 0.4. So what you do is you basically travel along the wet bulb line, reach the saturation, read the enthalpy from there. Let's say here it is 72, and then you add whatever is the deviation. So deviation is minus 0.4, so you add minus 0.4 and you get 71.6 kilojoule per kg dry air. This is the enthalpy. So yeah, that's enthalpy deviation, and this is the enthalpy at saturation. Okay, enthalpy. Relative humidity we have discussed, absolute humidity we have discussed. Humid volume. Now, okay, this graph has become clumsy, so but still we'll manage. Let's try another color, orange maybe. Okay, yeah. So you see these lines over here. These are constant volume lines, quite far spaced apart. So if you want to get something in between, you need to take an average. So wherever you are, let's say you are here, over here, and then it says what is the humid volume. Humid volume is 0.95. Again, what are the units? Humid volume units are meter cube per kg dry air. So see, everything is defined in terms of kg dry air. So 0.95 meter cube per kg dry air. That's humid volume. And adiabatic cooling, as the name suggests, you pass air, let the water cool down. Or in other, or let's say here I have a different task. Let's say I want the air to cool down. So I already have water at, let's say, wet bulb temperature itself, wet bulb temperature. Okay, let's say the water is already at wet bulb temperature. I pass air, I pass water, water comes out, air goes out, and this air temperature is of course lower than this air temperature. So since you are not adding any heat from outside, it is called adiabatic cooling. So you are cooling air. So what we say here is that if the temperature difference in water, it is called sensible heat. Sensible heat is the heat required to change the temperature. If the temperature difference is water is less than, or the sensible heat required to do the temperature difference in water is less than enthalpy change due to vaporization, then we can say that adiabatic cooling follows exactly the wet bulb line graph. So basically, if the dry bulb temperature is here and you go for some cooling, the temperature will vary along this. The temperature and humidity will vary along wet bulb lines. And finally, the minimum possible temperature again is the wet bulb temperature. Yeah, so need to keep this assumption in mind. So see, if it is already the water is already at wet bulb, it cannot go lower because wet bulb is the lowest possible. If it is near wet bulb, you can say that if the temperature difference is low of water in and water out, and H vaporization is very high, which is 540 calorie per mole, so it's quite high. So you can say that we can use this assumption, and adiabatic cooling goes along the constant wet bulb lines. Okay, we have talked about all the terms, and that's all for this video. Thank you.